Hello, in this video we're going to solve for the capacitance for a spherical capacitor. So what we have is a conducting conducting sphere in the center with a radius of A, and then a spherical shell of radius B. And these two objects would not be touching. Realistically, there would be some type of insulating material in between them and holding them together. But we're just interested in those shells. The inner sphere is charged positive Q. Alright, so we need to determine the electric potential difference between points A and B. Alright, so if the inner sphere is positive Q, we have an electric field that is radiating away in between the space here. And we know that that's going to drop off as a function of the distance away. So to find the electric field strength in between there, we would draw a Gaussian surface at some point in between. And start with Gauss's law. The area that we'd use is the area of our Gaussian surface, which is a sphere. So we have E dot 4 pi r squared equals the total charge enclosed, which is the total positive Q over epsilon naught. So we know that this acts just like a point charge, and the electric field is 1 over 4 pi epsilon naught times Q over R squared. Now from here, we need to calculate the electric potential. We needed the field to figure out the potential. So the potential difference is the negative integral of E dot ds, and we're going to go from point A to point B. For this, we're going to substitute the value of our electric field into that integral. And pull out all the constants. Oh yeah, this is dr. I lost all my spheres here. Oh well. So we have 1 over 4 pi epsilon naught. That should be Q over 4 pi epsilon naught. Integral from A to B of 1 over r squared dr. So we know that that integral is going to be 1 over r. It's actually going to be negative 1 over r, which cancels out that negative sign, and we're going to evaluate that between A and B. So we have Q over 4 pi epsilon naught, 1 over B minus 1 over A, and again, that is the change in potential. And to simplify this a little bit further, we would multiply the bottom by, or the left term by A over A, the right term by B over B. So we end up with the change in potential from A to B is going to equal Q over 4 pi epsilon naught times A minus B all over A times B. Now that's actually all the old stuff that we were doing in chapter 24. The new stuff here is by just applying the relationship for a capacitor, which is Q is equal to C times V. To solve for the capacitance, we're going to rearrange that equation, so it's going to be Q over V. just going to substitute in the equation that we just found. So we have Q over 4 pi epsilon naught A minus B over AB. Alright, try to clean this area up a little bit. Alright, move that over. There we go. So now just math that. Alright, so the Q's cancel. The bottom flips up to the top. So we have 4 pi epsilon naught times AB over A minus B. And that is going to be what the capacitance is equal to right there. Alright, so the last step, just plugging in our electric potential that we find using the method from Chapter 4. Just plug it in that equation and solve it for C. We're going to look at solving for a cylindrical capacitor in another video.